Hi, hello, this is Chemistry at Glance and my name is Aneta. If you're new with my name, I left all the links in the description box below with the links to my blog and the links to the sections where I explain something about myself and what I do here. But today's video is all about naming organic compounds and the types of formulae and homologous series. If you're new to this topic or you want to revise it first before answering the questions, just click on the links below and it will direct you straight to my blog page where I explain this topic. Also, if you would like a copy of these questions to go through them with me, just let me know somehow. Email me, leave a comment or anything and I will get back to you. Okay, so we've got the first question here. Compound X contains carbon, hydrogen, and oxygen only. 1.55 grams of compound X was burnt in excess oxygen and 1.86 grams of water and 3.41 grams of carbon dioxide were formed. Nothing was lost during the reaction. And the first part of this question asks us to calculate the empirical formula of compound X. So what you want to look at first is that our overall equation. You don't have to be specific, just saying compound X plus oxygen gave us water and carbon dioxide. It's just for us to visualize it before we carry on with the question. So we are told that we had 1.55 grams of compound X and 1.86 grams of water was produced and 3.41 grams of carbon dioxide were produced. So, of course, we want to find the empirical formula of this, and we know that compound X consists of carbons, hydrogens, and oxygens only. So we've got our carbon right here and our hydrogen right here. So what you want to do is find the percentage of hydrogen in this compound X. Because nothing is disappeared, whatever amount we had of hydrogen here, we had to get out because nothing was lost. And whatever amount of carbon we had here, we have to have here. So what you want to do is find the number of moles of hydrogen on this side and carbon on this side. And then calculate the percentage, or actually if you find the number of moles and then you use this number of moles to find mass of hydrogen in water, you can find the percentage of hydrogen that was here. Oh, do you know what? I'll just start with a question and I hope you'll follow it. So firstly, H2O. The MR of H2O is 18. But the MR of H2 in H2O is 2. So the percentage or the fraction of hydrogen in water is 2/18. Therefore, we can consider this as being the number of moles. Because, sometimes in this equation, you can use N as, for example, a percentage, and in this example, we're going to use it as a fraction. So we're trying to find the mass of hydrogen that was produced, because that's going to be the mass of hydrogen that was at the beginning, because nothing is lost. So our mass is N times MR. Our N in this example is 2/18, our fraction of hydrogen, times it by the MR of hydrogen, times it by I think it's going to be easier to explain it other way. So forget this. We have our fraction of hydrogen in water. So if you want to find how many grams of water there are, you actually can just times it by 1.86. because 1.86 was the mass of whole water. And now we found the percentage of hydrogen. This is much easier way. So we have the percentage of hydrogen in water, which is 2/18, and that's the mass of water. And this gives us 0.207 grams. What I did is basically times the mass of water times by the part that is just hydrogen. So now this is the mass of the hydrogen in water. And now we have to do exactly the same thing with carbon dioxide. So the MR of carbon dioxide is 44, but the MR of carbon is 12. So our percentage of carbon in CO2 is 12/44. This is our percentage of carbon, and carbon dioxide weighs 3.41, and this gives us 0.93 grams of just carbon in carbon dioxide. Sorry about this confusion, but I found that way might be much easier for you to understand. So we've got both masses of carbon and hydrogen that was created. Now we have to find the percentage of this mass compared to compound X. So what you want to do is do this, 0.207 grams over 1.55 times 100, because we want to find a percentage. That's the mass of hydrogen over the whole compound, and this gives you 13.3%. The same with carbon. 93 grams over 1.55 times 100, and this gives you 60%. That's the percentage of carbon in compound X, that's the percentage of hydrogen in compound X, but we are told that it also contains oxygen. So these two percentages added together gives us 73.3%. So the rest up to 100 will be the oxygen. So 100 minus 73.3 gives us 27.7% of oxygen. As we do in the empirical formulas, we want to find the ratio. And to find the ratio of carbon, hydrogen, oxygen, you do percentage over the AR, that's for carbon, 13.3 over 1, that's for hydrogen, and 27.7 over 16, that's for oxygen. And this gives us 5 to 13.3 to 1.67. We divide it by the smallest, so every single number we divide by 1.67, and this gives us a ratio of 3 to 8 to 1. Therefore, our empirical formula is C3H8O. This was a long way to come to this, but this question definitely is with a lot of marks. The second part of this question says the MR of X is approximately 65. What's the molecular formula of X? So we have the empirical formula, which is the simplest ratio, and molecular formula is the actual ratio of these atoms. So we are told that the MR of compound X is approximately 65. So what we want to do is calculate the MR of C3H8O. And this is 3 times 12 plus 8, because one hydrogen is 1, plus 16 for oxygen, and this gives you 68. 68 is approximately 65. Therefore, the molecular formula will also be C3H8O. These next questions are short ones, so there shouldn't be any problem with them. State the systematic name of compound Y. This is compound Y, whose structure is like this. So, the first thing you want to do is calculate the longest chain of carbons. So we could either do 1, 2, 3, 4, or we could do 1, 2, 3, 4. Either way, we're going to have the same compound. So let's do it like this. What I mean by saying it's going to be the same compound is that if we do 1, 2, 3, 4, then we're going to have a CH3 group on the second carbon and Br on the second carbon. If we do it like this, 1, 2, 3, 4, we're still going to have a CH3 on the second carbon and Br on the second carbon. So it doesn't matter. So we've numbered our carbon atoms. We know it's 4, and 4 carbon atoms means it starts with but. It's butane, but we also have this bromine and this methyl group, so we have to add them in as well. So our methyl group is on second carbon and bromine is on second carbon as well, but we have to put it in alphabetical order, so bromine comes before methyl. So we got 2 bromo, 2 methyl, butane, and that's all. Next question, compound Y, this is compound Y, this is compound Z. Compound Y, this one, reacts to form compound Z, this one. And now we've got to name this compound. So again, we have our methyl group, and we have to name the order the carbons. So you go 1, 2, 3, 4 carbons. So again, it's butane. We don't have our bromine anymore, but we have a double bond. Double bond means it's no longer butane, it's butene. But obviously we have our methyl group still on the second carbon. Oh, as well, in this one, we couldn't number these carbons in the order like this, 1, 2, 3, 4, because the branches, so our functional groups, has to have the smallest number possible. So in this example, we couldn't do it like this, 1, 2, 3, 4. We have to do it 1, 2, 3, 4 this way, because we have our first functional group, which is alkene, double bond, right on this first carbon. So alkene is on, double bond is on the first carbon, our methyl group is on the second carbon. So what you want to do is write 2 methyl, and then but, you can say 1 because it's on the first carbon, ene. We always put the double bond in the last part of the name. Okay, now we are asked to draw the displayed skeletal and structural formula of but2-ene. So it's but, so we know it's going to be 4. We're going to draw the displayed formula first, because I think it's the one that if you draw it, you straight away know what's going on in the equation. So we got 2-ene, so we've got an alkene on the second carbon. You can do it from this side or from this side, it doesn't matter, because it's still going to be in the middle. So we have our hydrogens right here and our hydrogens right here, but because we have a double bond, we're only going to have 2 hydrogens and not these ones. Now the skeletal formula, in skeletal formula, you basically draw the skeletal of carbons. So you have 1, 2, 3, 4 carbons. So you got 1, 2, 3, 4 carbons. And now we have to highlight that on the second carbon, we have this double bond. Next one, 3-methyl hex 1-ene. So hex means 6. 1-ene means double bond. 3-methyl, if we started 1 from this side, we do 1, 2, 3. You can't do it like you put 1 here and then you count from the other side, 1, 2, 3, and put CH3 right here. You have to always count from the same side. So we only have 2 hydrogens on this bond, 1 hydrogen on this one, and then just carry on writing the hydrogens around. And our skeletal formula of this one is going to be 1, 2, 3, 4, 5, 6. Double bond on the first one, 1, 2, 3. On the third one, we've got CH3. Oh, I forgot to write the structural formula. So the structural formula means that you have to write everything that's in a compound. So we've got CH3 first, carbon by carbon you go in. and CH and another CH. So we can do a bracket and a 2 and then another CH3 at the end. For this one, you've got CH and a CH, so 2 CHs again. Oh, sorry. No, it's not. Because we have 2 hydrogens here. So it's CH2, CH, CH3, CH, C3, CH. Then you've got 1, 2, CH2s, 2 of them, and then at the end CH3. Next one is 3-methyl pentan 3-ol. Pentan means it's 5, 2-methyl, and then pentan 3-ol. Ol is our alcohol, so on the 3rd carbon, OH. And for the rest of them, you just write hydrogens. And for the rest ones. And our skeletal formula is 1, 2, 3, 4, 5. That's the skeletal formula. We can add the groups, so 1, 2 on the 2nd carbon. You can just draw a line because it's CH3. You don't have to write a CH3, but you can if you want. And then on the 3rd one, 1, 2, 3, we've got our OH. And the structural is CH3, another CH3, so you can just write a bracket, CH. Then you've got another CH, so you can write bracket again, CH, plus an OH. And then you've got CH2 and CH3. Yeah, you should write the rest of the hydrogens. And that's all. Actually, we have 2 more examples. Tetrafluoroethane. Ethane means 2 carbons, but it says tetrafluoro. So we just add fluorines. I think I should say ethene. Double bond right here. Our skeletal is going to be 1, 2. And that's all for this one. And with a double bond, because we have double bond. And now difluoroethene. That still means double bond with 2 carbons, but we only have 1, 2 fluorines, and the rest is just hydrogens. Skeletal formula will look exactly the same again. But our structural formulas look different because we have CF2, F2 in this example, and in this example we've got CFH, CFH. You could also write CHF and CHF, it doesn't matter. Okay, the next question says, the compound below has a cherry odor and is used in the manufacture of fragrance agents. This is our compound. Name the functional groups present in this compound. So our functional groups, there's actually 2 functional groups in this example. One of them is our alkene, and other one is our alcohol. State the molecular formula of this compound. Molecular formula is the ratio of each atom in a compound. So we've got C's and H's and O, and then you just gotta find how many of each there are. So we've got 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5, 7, 8, 9, 10, 11 hydrogens. I think I counted that wrong. 1, 2. We've got 5 here. 6, 7, 8, 9, 10. See, I'm not counting right. And then oxygen. And that's the finished question. This is our very last question. A section of an addition polymer is shown below. State the systematic name of the monomer that gives this polymer. Okay, so we have to name the monomer that gives this polymer. I know the polymers is not a topic I went through yet with you guys, but I'm sure you know this from your GCSEs as well. So polymer is this, but monomer is going to be just this one section. So when these bonds are not open yet, that means the monomer has a double bond between the carbons. And then it's CH3, H, H, CH2, CH2, CH3. So what you want to do is find the longest chain of carbons. So in this example, we have 1, 2, 3, 4, 5, 6. This is our longest chain. So you can name these, number these, sorry. You know that 6 carbons gives you a hex starting. And the next thing you want to do is look for the functional groups. The only functional group we have on here is our double bond. We can't go like this, 1, 2, 3, 4, 5, 6, because that means our double bond will be on 1, 2, 3, 4th carbon. If we go from this side, our double bond will be on the 2nd carbon. This is the smaller number. That's why we're gonna number it from this side. So we've got our hex. It's an alkene, so it's gonna end with E, but it's on the 2nd carbon, so it's gonna be hex 2-ene. These are all the questions from me today. Remember, everything I show you are my techniques and ways of learning and revising. If you have any questions about my videos, please comment or email me. I leave all these links in the description box below, as always. Also, if you have any comments about the quality or content of my videos, please also leave them under this video. Thank you. And for now, like, subscribe, and see you soon. Bye.